Welcome to Basic Brewing Radio for Thursday, March 24th, 2011. I'm James Spencer. Here at Basic Brewing Radio, we're all about home brewing. With this week, part 2 of Kai Troester's presentation on pH. This week, Kai gives us his take on how not only water, but the grist of the mash contributes to the pH of the beer. If you're new to home brewing and would like to get into the hobby for the first time, check out our website, basicbrewing.com, where you can find archives of our audio and video podcasts and our DVDs to walk you through basic and more advanced brewing techniques. You can also find our brewer's logbooks to help you track the details of your brews. You can follow me on Twitter. I'm Basic Brewing, all one word. On Facebook, I'm at facebook.com/basicbrewing.james. And our show page on Facebook is at facebook.com/basicbrewing. Thanks again, everybody, clicking on the Amazon.com associate link on our basicbrewing.com site. Whenever you think of Amazon, think of us and click on our associate link first. It won't cost you any extra, and you'll be helping us to bring you this show, and we appreciate your support. We also have associate links for Brew Your Own magazine and the American Homebrewers Association on the site, too. And you can find our Basic Brewing iPhone and Android podcast apps on their respective stores. And we're in the BlackBerry podcast directory, too. Kai covered a lot of material, so I want to get to it quickly. But first, I want to remind you that we're looking for experiments to conduct and or evaluate at the Homebrewers Conference in June. I've received some suggestions already, but I'm greedy. If you're going to the conference in San Diego and want to perform an experiment either alone or with your club, please drop me a line and let me know, and we can get together. In the news this week, I received news through Facebook from Oregon. Good news from Oregon. Lars writes, Governor Kitzhaber is scheduled to sign SB 444 into law on Monday, the 28th of March, 2011 at 3:30 in the afternoon, after which it will again be legal to transport legally homebrewed alcoholic beverages for all lawful purposes in the state of Oregon. That's awesome news. Congratulations to everybody up there. At the same time, on the other side of the country, there's another legal challenge for beer lovers. I received a note from a D.C. homebrewer that says, last week, D.C. Brow, the first packaged brewery to operate in the district in 50 years, brewed their first batch. Antiquated laws in D.C. currently don't allow any type of permit for a tasting room on the premises of the brewery, so they would be able to do tours but not offer a sample at the end. That's a bummer. There's currently a bill before the D.C. Council to change that. Any listeners in D.C. should contact their council member and ask them to support the Brewery Manufacturers Tasting Permit Act. So that it sounds like a good thing to do, because the funnest thing about a brewery tour is having a little sample at the end. So good luck with that. So it's kind of like whack-a-mole. You get one legislative issue taken care of, and there's another one to take its place. Now let's jump right into the meat of the matter this week with part 2 of our conversation with Kai Troester on pH in the mash. Well, Kai Troester, welcome back to Basic Brewing Radio.
Oh, thanks for having me on again.
Now, this is the second part of a two-parter. Last week, we talked about pH and kind of gave the basics of what pH is and started to talk about the role that pH has in the quality of our beer. But this week, we want to delve into kind of the more practical side and some experiments that you've been doing, right?
Right. Yes. It was. I think it started in about 2008 or beginning in 2009 when I just thought about, well, what about investigating how the grist and water affect pH? Because at that point I felt there was a lot of arm waving done or hand waving when it came to, well, how really is this effect, and trying to quantify this effect. And I ended up doing a lot of very small mashing experiments. So I would use about 12 grams of pulverized malt, and I would mix that with generally on the order of about 50 or 40 or 50 milliliters of water, and I would have a lot of these samples, and I would mash them for a short time in a water bath, and then I would cool them to test the pH. And so by doing that, I was able to obviously evaluate a high number of mashes. and I didn't really have to obviously really brew a beer out of all of them.
Mm-hmm. Now, I'm assuming that the results from that small mash scale up to a larger mash. I'm assuming that you've done a test to ensure that the smaller mashes actually depict what's going on in the larger one.
Well, to some extent they do. So to some extent I feel they don't really, but I was able to discover some interesting mechanics, I would say, behind mash pH that so far have been neglected. And I'm also continuing to look into that because this is such that every time I answered a question, I kind of found two more questions to be answered.
Of course.
So it's like you open that Pandora's box of questions there, and so I keep thinking about mash pH. I keep experimenting with it, and also I keep very detailed notes about the mashes I do, and I'm trying to correlate those with what I found, and in particular also try to correlate that how well that does this work with this algorithm I found for predicting mash pH out of the grist composition and the water composition.
So it's not just water. I mean, everybody's worried about the pH of their water, but it's more than just the water.
Yes, and I found that actually it is the malt that sets most of the pH, and that water compared to what mechanics are going in there with the malt seems to be the simpler part of the equation. That's, as I said in last week's show, I explained the idea of a pH buffer, and that's what the malt is doing. The malt is a pH buffer that is created by the mostly proteins and amino acids, and to some extent the phosphates in the malt. And it is so well buffered that in most cases, the malt just sets the reasonably correct pH, and that the water doesn't really end up being able, or that the water is not really able to change it all that much unless the water is somewhat on the extremes, on the extreme ends. And I will talk about that later. And the good thing about seeing that mash as a buffered system is that it makes the math much simpler, as we can approximate the pH changes by just using linear functions, by just exploiting the fact that pH is proportional to the amount of acid or base added to the mash, and it's inverse proportional to the concentration, so the mash thickness. And in the end, the math is all about accounting for the acids that were added and the bases. Bases are things that can neutralize acids, and those things would come either from the malt, they can come from the water, or they can come from additions that we make to the water, to the mash or water.
So where do we start? How do we start thinking about, say, the grist of the malt?
Well, yes, that's it. I think I like to start with just the grist, and the idea of that the grist has a pH, because I like to think about the fact that the grist has an inherent pH of its own, and that the water tries to change that pH. And it's also such that the grist is largely determined by the type of beer we want to brew. It's not really like in the olden days where brewers were kind of matching their grists to the water they had in hand. They would find out that some types of beers or some grain combination or malt combinations would work better with the water that they have compared to other combinations. But we brewers like to have a lot of variety, and we don't want to be limited by the water that we have. So we like to change the water to then match what we have as the grist. And in my experiments, I found that very pale malts, like the Pilsners and the just regular two-row brewer's malt, they give a pH of about 5.7 to 5.8 when mashed in distilled water. And the kilning process used to create darker base malts, that creates melanoidins, which react acidic and they are lowering the pH. So what I did, I took a number of base malts. I think I at the time I had about probably 15 different base malts samples to test, and I tested their pH in a distilled water mash. And the idea of using a distilled water mash is that there are no minerals brought in through the water that would change the pH. So you would kind of get that inherent pH of that grist.
Mm-hmm.
And I had looked a few of the examples I had. For example, Pilsner, it tested at 5.75. Maris Otter was very similar. It had a pH of 5.77. Then I also had Raw 2 Row, which was an odd malt because it is a very light cotton-colored malt. It's like a regular 2 Row brewer's malt, but it had a pH of 5.56, which was 0.2 lower than what I got from other malts of that color. It was a pH that was closer to Vienna malt. And the Vienna I had at hand had also a pH of 5.56. And then the darker malts, I tested Weyermann's Munich Type 1, and I got a pH of 5.3. Oddly enough, the even darker Munich malt, the Type 2, had a higher pH. Its pH was 5.43. And while these are just samples and that other batches of malt may differ significantly, it kind of shows that tends to be a correlation that the darker the malt, the lower its pH, but it is a fairly loose correlation, and that there are quite a number of exceptions to that rule.
So if you're thinking about brewing a certain style of beer, you may be able to predict the pH of the mash, but not necessarily.
Well, you can somewhat predict the pH of the base malt based on its color. You can get a very good idea of where it should be. And at the end, what we were talking about, the differences here that I saw is like a difference of 1/10 or 2/10. That's not all that bad in terms of precision. But so if you're mixing these base malts, I like, for example, to brew a lot of beers where I mix base malts in order to get the color. And it's fine to just take the weighted average of the pH, and that turns out to be then the distilled water pH of that grist that you're getting. But I also tested specialty malts. And those are more interesting when it comes to creating color in beer. And I tested them differently than the base malts, because the specialty malts tend to be more acidic than base malts. I made small mashes, and I titrated these mashes to a pH of 5.7. And the idea of titration is that you take, in this case, a strong base, and you keep adding that to that mash until the pH rises to a set endpoint. And the amount of strong base that I had to add there is a measure of the acidity that this base malt has. So basically, it's a measure of the amount of acid that this base malt brings into the mash, and the amount of acid that is able to lower the pH of the mash. And when I plotted the acidity of the base malt over the color of the base malt, I found two distinct groups. And the first group were crystal malts, where I found a fairly linear relationship between the color of the malt and the amount of acid that is per unit of grain weight. But when I looked at the roasted malts, across the color range that I had there, which I think ranged from about 300, 400 Lobberband all the way to 600, 700 Lobberband, the acidity didn't change much. The acidity stayed around the middle of the range that I was able to get with the crystal malts. And that showed me that roasted malts have less acidity per color than than crystal malts, and that is an important thing to take into account when trying to estimate pH or the grist pH from the beer color. So, as I just touched on, beer color and grist acidity or grist pH are fairly closely related. And the formulas that are used to calculate them, they're also very similar, and it's possible to create a fairly reasonable, accurate formula that takes in the grist, that takes in the color of the beer and predicts what would be the distilled water pH of that grist. And obviously, a grist that contains a lot of crystal malt will have a lower pH compared to a grist with a lot of roasted malt, because the crystal malts have more acidity per color than the roasted malts. For example, if you take a crystal malt only beer, like let's say two-row and crystal malt, and when the color of that beer increases by just 5 SRM, the pH of that grist drops about 1/10 pH points. But if I make the same thing, if I do the same thing with a beer that has that uses the two-row and only roasted malt, I need to change the color by 13 or around 13 SRM to get the same pH drop. So because of that, it's important to not only consider the color of the beer in such a formula, but also consider the percentage of color that is coming from roasted malt.
That's interesting. So you can use, in addition to using chemical additions to your water, you can use the profile of your grain bill to adjust your pH as well.
Yes, you can, and that goes back to the idea that you can actually tailor, or you can make you can make a grist that would work well with your water, but it would, after a while, it would kind of be boring if a person who has very hard water, like but no, a person that has water that has a lot of alkalinity. There's not necessarily a correlation between hardness and alkalinity, and I'll get to that later. But a person that has a water that is a lot of alkalinity, which tends to raise the pH, it would kind of, after a while, be boring to making stouts all the time.
Right.
So we do want to take charge of the water. And that formula that I talked about, I did implement that in the water calculator spreadsheet that I have, and I also know that it's implemented in the easy water calculator, but I'm not sure really to what extent that is implemented there, and because I keep changing it a little bit as I find problems with it.
Now we have a question along those lines from Sean Terrell, our friend Sean Terrell. What are Kai's thoughts or experiences with the RA equals 4.5 times SRM correlation? Is it sufficient for most beers, or would he recommend always using a tool like your spreadsheet that I assume we find on your website?
Well, you don't really have to use like a tool like the spreadsheet. I mean, there are like on my website I also have tables where you can look up the color, where you can look up what residual alkalinity of the water is necessary compared to the color and percentage of roasted color. But we mentioned RA, which is the abbreviation for residual alkalinity, and I'll get to that later. That is something that's coming from the water. But he's mentioning a formula where we multiply the color of the beer with a factor, and the problem with that formula is that I don't expect it to work at all for very lightly colored beers, because for those beers you actually need negative residual alkalinity, which you wouldn't be able to get from this formula. And also, this formula is not taking into account the mash thickness, which can have a fairly strong impact on the pH, depending on the water. And it also does not take into account the difference that exists between roasted and crystal malts.
Now, maybe we should before we get too far into the details, should we ask us a simple question? For instance, from Facebook, Chris asks, "How do I know when I should be concerned with pH?" I mean, we're about to get into a bunch of details of fixing your pH or manipulating your pH. How do you know when you have an issue?
Well, that's a good question, and that's a question that comes up a lot because there's a lot of talk about mash pH on brewing boards because we brewing geeks need something to talk about. But yeah, so when would you have to be concerned about pH? And I would think that if you're getting astringency, for example, from your beer, if you get this puckering feeling, this dusty feeling in the back of your throat, that can be related to excessive tannin extraction during sparging. You may want to worry about pH if you're getting less than expected efficiency, or if your conversion performance in the mash is not as good as you hoped it to be, because mash pH has a direct impact on the enzymatic activity. You also may want to worry about pH if the bitterness that you're getting from your hops is rather harsh, because that could be because the boil pH is too high and you're getting more that harsh rather than that soft bitterness. And lastly, if the beer just doesn't taste right, if the flavors are not really bright, if they're more muddy, if they don't really shine through, there's a good chance that taking care of the mash pH, which then sets the stage for the pH and all the subsequent stages, taking care of that helps a lot. And a lot of that starts with getting an analysis for your brewing water.
So let's move on to it. So basically, if you like your beer the way it tastes, if you like the efficiency that you're getting out of your mash tun, if everything seems to be going all right, maybe you shouldn't worry about pH. But if at that point you want to tweak your process a little more and try to get a little more out of your beer or to see what happens, then you can start playing. I guess one of the places that you can look, in addition to your grain bill, is the water.
Right. I mean, the one thing I wanted to add is just, even if you like your beer right now, if you're looking for something, how could I possibly improve my beer? You could start looking at pH, could start trying to find things to measure pH, like the strips I mentioned last time. They are a fairly cheap way of measuring without committing to like a $100 pH meter.
Mm-hmm.
So I mentioned that water is oftentimes the culprit in pH problems, and that's because we don't use distilled water for brewing. And water that we get from the tap usually has minerals in there that can affect the pH. And in particular, those minerals are calcium, magnesium, and most importantly, the bicarbonate. Now, as I said earlier, that it's not just the concentration of these minerals that matters, but it also matters how much water per unit of grain are you adding to the malt, because the more water you add, the more minerals you add, so the more they can affect the pH. So that means the effect of the water on pH also depends on mash thickness.
Mm-hmm.
Now, that may lead some people to think that if I have mineral-rich water, and I don't want it to affect my pH or that much. All I have to do is to just mash thick. Well, that may work for the mash pH, but the problem is that all the water that you're not using in mashing, you'll use for sparging. So
Yeah.
you'll end up adding all these minerals anyway.
Yeah.
And they may cause problems during the sparge step, and that may cause problems during the boil by getting the pH in these steps out of whack. So of the minerals, I mentioned that the bicarbonates are generally the most important ones when it comes to effect on pH. And that's because the bicarbonates, they act like a base. And I said a base is something that can absorb hydrogen ions, so which leads to raising the pH. And in water reports, the bicarbonate content, or the water's ability to neutralize acid, is generally expressed as what's called alkalinity. And alkalinity is actually tested by taking a sample of water and adding to it acid until the pH reaches 4.3. Now that 4.3, that can be different, but it's generally around that pH. So now the amount of acid that had been added is a measure of how much ability did this water have to actually neutralize acid. And it's just like what I did for specialty malt, just the other way around. For specialty malts, I added a base to measure how much acid does this contain, and here they basically add an acid to see how much of a base does this water contain.
That makes sense.
Yes. And and the other two minerals that I mentioned were calcium and magnesium, and their effect on mash pH is a little bit more complicated and less intuitive. What they do is they can react with with phosphates that are brought in through the malt. The malt contains about 1% by weight phosphate. This is quite a lot. And what they do, they form insoluble calcium and magnesium phosphate salts. And as those salts form and precipitate and basically go out of solution, what's left over are hydrogen ions. And those hydrogen ions act like as if you added acid to the mash, and they thus they lower the pH of the mash. So if you add calcium or magnesium, the effect is that it lowers the pH. And in the early 20th century, a number of German brewing scientists around Kolbach and Windisch, they figured out that the calcium, magnesium, and bicarbonate in the brewing water, that affects pH. And they also figured out that the calcium and the magnesium have the ability to actually counteract the pH rising effect of the bicarbonate. And what they found is that it takes about 3.5 calcium equivalents or 7 magnesium equivalents to neutralize 1 equivalent of alkalinity. Now, I don't want to get into the details of what's an equivalent, but it's the idea to actually express the amount of something, not by its weight, but basically by the amount of pieces that are in there, basically by the amount, the actual number of ions. And what they defined is residual alkalinity, that is the alkalinity of the water that is left over once you consider the calcium and magnesium acidifying reaction. So, and that's what brewers commonly abbreviate as RA, and that comes up a lot when they talk about water, because it's that residual alkalinity that's left to change the pH of the mash. And to calculate it, you would just subtract the calcium hardness divided by 3.5 and the magnesium hardness divided by 7, you would subtract that from the alkalinity, and you would get the residual alkalinity. If your water report only contains the alkalinity and what's called the general hardness, so it's the hardness from both the calcium and the magnesium, you can actually estimate residual alkalinity by subtracting the general hardness divided by 4, subtracting that from the alkalinity. And that works out very well because most of the time, about 30% of the hardness is from magnesium and about 70% from calcium. So if you do the math, you come up with about a quarter of the general hardness that has to be subtracted from residual alkalinity. And the value of residual alkalinity is that it gives you a means of assessing the water and the effect it can have on the pH. If the water has a residual alkalinity that's greater than 0, and that means that it can raise, or it will raise the mash pH compared to the distilled water pH of the grist that we talked about earlier. If the water has a negative residual alkalinity, that means there's more acidifying, so there's more left over from that calcium and magnesium reaction than there was necessary to actually neutralize the alkalinity or the bicarbonates. And that kind of water is able to lower the mash pH. And if the residual alkalinity is 0, then ideally that water doesn't change the mash pH at all. And while we take a lot of that from the work that was done by Kolbach and others, it should be pointed out that their work actually didn't focus on mash pH. Their work focused on the cast out wort pH. So basically the pH of the wort that goes into the fermenter. And that, I think, seems more important to many German brewers, and it's such that if that pH is correct, generally the mash pH was correct too, and also the relationship that a 10 and a change in residual alkalinity of 10 parts per million as calcium carbonate, which is a measure of alkalinity, that such a change would lead to a mash pH change of 0.016 units, is derived from his work, but was incorrectly applied to mash pH. Because it actually doesn't really apply to mash pH, it applied to the cast out wort pH. And in my experiments, I found that in order to change the pH by 1/10 pH unit, it takes about 3 to 5 milliequivalents of an acid or base per kilogram of malt. So I found that it's better to express what it takes to change the pH. It's best to express that based on the weight of the grain, which provides that pH buffer, rather than using the amount of water in there. And there's this milliequivalence of acid or base is somewhat of an abstract number. If you convert that to lactic acid, let's say 88% lactic acid, it means that it takes about a quarter to a little under half a milliliter of 88% lactic acid per kilogram to lower the mash pH by 0.1 pH units. And if you work with pound, we'll just take half of that.
So we're not talking about a tremendous amount of lactic acid adjustment there.
No, we are not talking about it. And that amount of lactic acid, that also doesn't really show up in the flavor of the final beer. And by thinking about it in that way, it also takes care of the mash thickness, because you're not really basing the lactic acid additions based on the amount of water you add. You're basing it on the amount of grain you have. So now that we know, well, how is the mash pH set by both the kind of inherent pH that the grist has and the ability that the water has to change that pH through its residual alkalinity. The question is, well, what to do if the predicted or expected mash pH doesn't fall into the desired range between 5.3 and 5.5. And in most cases, the pH will be too high, the mash pH. And that's because the water has too much alkalinity, or too much residual alkalinity, better said, and the the grist provides too little acid. There's basically too little color in there to counteract that residual alkalinity. And so the brewer has a few options to reduce that residual alkalinity. The first option is, well, just to dilute that water with low alkalinity water. So that's basically, depending on the rate of dilution, that alkalinity will go down. But you have to keep in mind that you're not only lowering the alkalinity, but you're also lowering all mineral contents, all mineral concentrations. So it might be beneficial to add back some minerals, in particular calcium, which is fairly beneficial for many brewing steps, other than its ability to lower mash pH. But another option to lower that alkalinity is to neutralize the bicarbonate, either completely or partially, through the addition of acids. And there are two acids that are very popular with brewers. The one is lactic acid, which also can be added in the form of acidulated malt. And then there's phosphoric acid. Both acids are fairly flavor neutral in the final beer. However, and they are also very, very safe to handle. And the other two acids that brewers may consider if they have access to food grade acids is hydrochloric or sulfuric acid. But those are strong acids, and those have to be handled with care. And the hydrochloric acid that you can buy in the hardware store, which is called muriatic acid, I'm not sure how food grade that is. It's very possible. It's very likely that in the production of acids, that the acid can easily dissolve metals and other compounds that you don't really want to have in a food product. So I don't use that for mash pH adjustment. I tend to use lactic acid, and I also recently started using phosphoric acid just to see what's the difference in taste. Now, another way to neutralize alkalinity is to increase the calcium content of the brewing water. And that increases that other side of the residual alkalinity equation. It increases the calcium hardness, which is subtracted from the alkalinity. And that's possible if the water doesn't have too much alkalinity, and if it doesn't have a lot of calcium already. So you can easily go up to 100 parts per million or 150 parts per million with calcium, particularly in ales, which are more flavorful. I like to keep the calcium in lagers. I like to keep the calcium usually around 50 to 70 parts per million. So it's not really a viable means for me to adjust mash pH or to counteract alkalinity. But yet another way to reduce alkalinity, and which is a fairly elegant one, is to reduce it through either boiling or treating water with slaked lime. And I don't want to go too much into the details of how this works and how it should be done. But what I want to say is that both processes, they are able to precipitate calcium carbonate, which is chalk, they're able to precipitate that from the water. And as it precipitates from the water, it pulls both bicarbonate, which is converted into carbonate, and it pulls calcium from the water to form calcium carbonate, and thus this process is actually able to remove minerals from the water and make the water less alkaline and also less hard. And when brewers talk about soft versus hard water, or when we talk about soft versus hard water, hardness is an expression of the amount of calcium and magnesium that you have in the water. It's not necessarily an expression, a measure of the alkalinity of the water, although it tends to be common that water that contains a lot of calcium and magnesium also has a lot of bicarbonates. But that idea of hardness comes from the fact that the calcium and magnesium inhibit the lathering of soap, and thus they make it harder for it to build up these suds.
Now, what if I get my water report and my water is just so crazy out of whack that I don't want to deal with it? Is there a way to build good water from scratch?
Yes, there is, and thanks to developments around reverse osmosis system and the fact that they have become fairly cheap, and many brewers are able to invest into them. So what those systems can do, they can actually take water that has a lot of minerals, and they can create a very low mineral water from it. And they do it by basically pushing the water through a membrane that has holes that are just large enough for the water molecules to get through, but the minerals, which are larger, they are not able to fit through these holes, and thus they get stuck, or they get then washed away on the other side. So with reverse osmosis system, you get very soft, almost distilled-like water that you can use as a blank canvas for your water, so to speak. So what you can do is now, once you have this very soft water, you would take brewing salts and would add them to the water to build a water profile of your liking. And many brewers are doing that, and that's where a lot of the, let's say, confusion is coming from, because suddenly you have so many variables to play with.
Mm.
And the salts that brewers use for that are in particular gypsum, which is calcium sulfate. They are using calcium chloride, then calcium carbonate, which is, again, what I said, is what precipitates when you remove alkalinity from water through boiling, but you can also add it back to put in alkalinity and calcium. And then also salts that table salt, some may add, because it adds sodium and chloride. But in most cases, that's not really added, because in excess, that can cause flavor problems. The beer may taste salty, but in low concentrations, it can enhance flavor. Another salt that is able to raise pH is baking soda, which is sodium bicarbonate, and compared to chalk, it is much more soluble. It's not as finicky when it comes to changing pH, and I'll touch on that later. How chalk is not, how predicting pH based on chalk additions is not that simple. And lastly, there is also Epsom salt, which is magnesium sulfate, and you wouldn't really use it for pH adjustments. Brewers just add magnesium and the sulfate to add some more magnesium to the water in order to, if they want to mimic a certain water profile, they may use that. So those salts are calculating the final water profile based on the addition of these salts is best done with a water calculation spreadsheet. It's not that the math is really complicated for that. It's just you have to keep track of all the ions that you added. Because if you add, you see, when you add a salt, you're always adding two minerals. You're adding an anion and a cation, and that means that, for example, you cannot increase calcium in the water without also increasing either sulfate, chloride, or bicarbonate. So once you have one of these water spreadsheets, you can then play around with the amounts of salts that you add, and you can then see what is the final ion concentration in the water. And in many spreadsheets these days, you can also then see, well, what's my predicted mash pH? And I said I do have a water calculator on my site that brewers may want to give a try, where you can enter the color of the beer, and you can also then enter the water and play around with acid additions and mineral additions and see how that changes the predicted pH. Now, I did mention chalk, and that was how chalk is tricky, and that was something that not only came out of my pH experiments, but that's an observation that also triggered some of these pH experiments. And this is that when I was playing around with chalk and using it in a spreadsheet, I noticed that the spreadsheet at the time, which was John Palmer's, didn't really give chalk all the alkalinity it should be able to actually contribute to the mash. And just before I was about to send John an email, I thought, well, maybe I'm going to design an experiment to see, well, is it really, I should design an experiment to see, well, is it really true that chalk contributes that little alkalinity? So, and I did, and to my surprise, I found that the spreadsheet was correct. Chalk did not contribute all its alkalinity to the mash, and the mash pH did not rise as much as I expected. So I was thinking, well, how is that? How does this happen? And then I also started dissolving chalk with CO2, where you can actually dissolve the chalk. You can put it back into the water. And when I did that, I noticed that, it suddenly has its full potential. So that is something that bothered me for a while, and just recently, AJ DeLang, someone who really knows a lot about water and water adjustment, pointed out to me that while the mash might be acidic enough to dissolve chalk, the time it takes to dissolve all the chalk may be much longer than what we give it. So, and actually, it seems to be true that chalk that is not dissolved in the brewing water through, for example, by adding CO2 under pressure, oftentimes, that chalk doesn't use its full potential, so to speak, of raising mash pH. And there have been accounts where people added chalk to the mash and didn't see a change in pH. And that, I think, I also attribute to that we should not assume that chalk easily dissolves in the mash. And I'll note that when we talk about pH pH testing and correcting pH during mashing.
But speaking of pH testing and correction, a question from Jeff. He says, how long should one let the mash rest before taking a pH reading?
Well, what I do, I usually let it rest to about 5 to 10 minutes, and then I pull a sample. I pull that sample with like a 12 milliliter vial that I also use for yeast culturing. I have that on a wire. I put that into the mash. I try not to get grain into it. And I cool, and in a ice water bath, I cool that sample down while having the thermometer in it and stirring it. And when it reaches around 25 degrees Celsius, I then dump that in a little dish I have and test it with my pH meter. And at that point, I hope that I'm at the pH that I want to be at. And recently I have been fairly successful with that because of history of past brews and because of the pH prediction in the spreadsheet. But if I would find that the pH is too high, I would want to add an acid like lactic acid or phosphoric acid. And again, it takes about a quarter to about a half a milliliter of lactic acid per kilogram of grist. And for phosphoric acid, I know that one of your listeners also had a question is, well, how much phosphoric acid to add to a 5-gallon mash to drop the pH by 0.4 units? Is that what he's asking?
Yeah. Chad says, how much acid should I add to my 5-gallon mash to drop its pH 0.4? I have phosphoric acid at 20%. Right.
So to get a drop of 0.1, you need about 3/4 to 1 milliliter per pound of 20% phosphoric acid. And you would have to, so that would be about 3 to 4 milliliters per pound would be needed to drop the pH by 0.4.
So Scott says, if you could settle on one mash pH, what would it be? I guess that's a basic question. What is your favorite mash pH?
Well, I like to be between around 5.4. I don't really worry too much if I'm still between 5.3 and 5.5. So yes, it's not really, I don't think that you really have to correct it down to the 10th or to the 100th of a pH unit. You can almost make slight adjustments the next time you brew that kind of beer.
Mm-hmm.
Because I don't like the hassle of running around and now getting stuff to add to the mash.
So,
I think we should also talk about what if the pH is too low, because that can happen too. And actually, I think that if your water is low on sodium, I don't think that there is a problem actually using baking soda to drop the pH, because compared to chalk, it readily dissolves in the mash, and you will get a more predictable pH change. So it takes about half to 3/4 of a gram per kilogram of grist of baking soda to drop the pH by 1/10. And I wouldn't really add more than about 1 gram to 1.5 grams per kilogram. You can also try chalk, but the chalk you may not see as much pH change than you expected. And if it doesn't really change at all, then there's not much reason for keeping to add chalk. So,
Parenta says, how frequently do you take pH readings in the mash, primary fermentations, barge water, bottling? How often do you take pH readings?
Well, I probably happen to take more than other brewers because I like to follow the pH through the brewing process. I do take sparge water pH readings on occasions. I've never really found. Well, actually, sparge water pH doesn't really matter that much. What matters is actually the alkalinity of that water, that sparge water, and because that alkalinity is what creates the water's ability to raise the pH during sparging. And you may want to check the pH during the sparge and make sure that the final runnings of your sparge, that the pH does not creep higher than 5.8 to 6. That's where people say that there usually you get excessive tannin extraction. And if you want to take care of the alkalinity in the sparge water, you can also add acid to the sparge water, but make sure that you don't add more acid than it's necessary to knock out that alkalinity, because all the acid that you add that in excess, that would just go towards lowering your pH even further, and your boil pH may be too low.
Now, we have another question from Scott. What effect, if any, does pH have on reducing DMS?
Well, that's an interesting question. I'm glad he asked. From what I know, DMS reduction is slower at a lower boil pH. But I haven't really heard homebrewers complaining about too much. So that's one reason why you may not want to go too low with your boil pH. I like to keep the boil pH around 4.5 at the beginning of the boil, and that generally drops to about it drops to about 5.25 to 5.3 at the end of the boil, and that's about a good number that I also read in technical brewing books as being a good target for the boil pH.
Now, anything else that you cover this topic in much more detail on your website, which I have links to if you look at last week's show and the description of last week's show on basicbrewingradio.com. But is there anything else? What are your final thoughts to take away in this episode? We've covered a lot of ground.
Yeah, I mean, my final thoughts are, well, just don't get too overwhelmed by this. Just give it some time and just read the different sources. Different authors may have different takes on how to explain it. And particularly if your beer is just fine right now, well, just take your time to go through it and take it step by step. Maybe you can improve the quality of your beer, or maybe you just happen to learn a lot of new things about just the science behind brewing.
So a good beer can become a great beer.
Yes, I mean, pH, or taking care of the water and taking care of pH can certainly make a good beer into an outstanding beer.
Awesome. Well, once again, Kai, I appreciate your help.
Well, thanks.
Well, thanks again to Kai. I'll be posting new links to pages on Kai's site in the description of this week's show on basicbrewingradio.com. Thanks again to all who sent in questions via Twitter and Facebook as well. If you have brewing questions, show suggestions, or just want to say howdy, write to james@basicbrewing.com, or just fill out the contact form on basicbrewing.com, and please don't forget to tell us where you're from. Our DVDs are on our site, Extract Brewing and Partial Mashing, also Stepping into All Grain, Low-Tech Lagering and Decoction Mashing, and Introduction to Wine Kits as well. And our 2011 Brewers Logbooks still in stock. We've got combo deals to save you a few bucks if you want to buy more than one DVD at a time on our site. And you can find our shirts, too. You can see a listing of the fine folks across our country who sell DVDs on basicbrewing.com. And if there isn't a vendor in your area, you can order them online in our online shop at basicbrewingshop.com. Thanks to everybody who's continued to click on our Amazon.com link. We appreciate the support there. Our featured products this week that were purchased through the link are Eats, Shoots, and Leaves, the zero-tolerance approach to punctuation, and the French Laundry Cookbook. Ancient French secret, ah? That joke is obscure for two reasons. Number one, I'm the only one who will understand it, and probably no one will hear it because it's at this part of the show. Thanks again, everybody. And remember, I can't tell who bought what, so no worries there. Just click on the Amazon.com logo on our site the next time you feel like Amazon shopping. We greatly appreciate your support. That's all until next time. Until then, thanks for listening, everybody. I'm James Spencer, production help for Basic Brewing Radio, and our website is provided by our buddy Kelly Dodson down in Austin, Texas. Basic Brewing Radio is a production of Active Voicing. We'll talk to you next time, everybody. So long.